Vibration analysis, balancing rotating machinery, techniques for ensuring smooth and efficient machinery operation. This presentation agenda will be including, balancing rotating machinery, introduction, preparing for the balance job, safety first, is the machine out of balance, balancing checklist, vectors and polar plots, overview, adding vectors, diagram placeholder, subtracting vectors, diagram placeholder, single plane balancing, summary, using vectors and single plane balancing, measurement setup, diagram placeholder, original balance run, adding the trial weight, selecting trial weight position. Trial run, interpretation, if trial weight is removed, balance solution, trim balance, splitting and combining weights, diagram placeholder, for run no phase balancing, two-plane balancing, overview, two-plane procedure, rule of thumb, balance standards, ISO 1940, ISO 7919, ISO 10816, summary, key points, final slide. This slide introduces the topic of balancing rotating machinery. Balancing rotating components is essential for minimizing vibration, reducing mechanical stress, and improving machine longevity. This introduction sets the foundation for understanding the engineering principles behind unbalance, the corrective techniques available, and the importance of proper procedure. The presentation will cover balancing fundamentals, methods, vectors, measurement techniques, trial weight methodologies, and balancing standards. It also highlights the role of proper preparation, safety measures, and diagnostic steps before balancing work begins. This slide outlines the agenda for the engineering presentation. It provides an overview of the topics including introduction, preparation steps, diagnostic evaluation, vector mathematics, single-plane and two-plane balancing procedures, selecting trial weights, evaluating trial responses, interpreting results, combining weights, multi-run balancing methods, and standards governing acceptable balance levels. The agenda ensures the audience understands the logical flow of the content and prepares for the progressive technical depth covered in the session. This slide discusses the purpose of balancing and why it is essential in rotating machinery maintenance. Unbalance produces centrifugal forces proportional to the square of rotational speed, leading to elevated vibration, bearing wear, seal failure, structural fatigue, and reduced equipment reliability. The introduction emphasizes that balance quality affects operational efficiency, energy consumption, and machine uptime. It distinguishes between mass unbalance and other vibration sources such as misalignment or looseness. It also explains that the goal of balancing is to minimize unbalance by determining the optimal correction mass and its placement. This forms the conceptual framework for all following slides. This slide addresses safety considerations prior to performing any balancing activity. It highlights the essential steps: lockout, tagout procedures, inspection of guards, securing tools, verifying rotational direction, and ensuring trained personnel are involved. Safety concerns include high-speed rotation, potential correction weight detachment, unexpected machine behavior, and electrical or mechanical hazards. Proper documentation, risk assessment, and understanding the machine's operational limits are indispensable. The slide also emphasizes the need to verify instrument calibration, ensure sensor mounting integrity, and review historical vibration data. Safety-first preparation reduces risk and increases the likelihood of a successful balance job. This slide explains how to determine whether unbalance is actually the root cause of observed vibration. Key indicators include high 1 times rotational frequency vibration, phase stability, minimal axial contribution, and similarity in waveform shape across radial directions. The diagnostic process involves comparing amplitude trends, confirming that other faults such as misalignment, looseness, resonance, or bearing defects are not the primary contributors. It also stresses the importance of checking for mechanical looseness and foundation issues. Phase measurements, vector interpretation, and amplitude behavior with speed changes help establish whether unbalance is truly present. This slide presents a comprehensive balancing checklist. It includes confirming instrumentation setup, selecting appropriate measurement points, verifying sensor placement, checking machine cleanliness, confirming trial weight availability, ensuring accessible correction planes, reviewing machine drawings, validating operating speed, and preparing vector recording sheets. The checklist ensures a systematic and repeatable balancing approach. It significantly improves the accuracy of measurements, reduces procedural errors, and ensures all prerequisites are met before running the machine. A structured checklist is a core part of professional CAT-2 balancing methodology. This slide introduces vector representation in vibration analysis and balancing. Vectors express both the amplitude and phase of vibration, enabling precise visualization of unbalanced forces. Polar plots show vibration magnitude as a radius and angle as phase relative to a reference mark. Understanding vector behavior is essential for balancing because correction weights modify the machine's vibration vector. The slide explains the significance of angular direction, reference orientation, and how vectors combine mathematically. Vectors are the foundation of single-plane and two-plane balancing calculations and critical to interpreting trial weight effects. This slide explains vector addition in the context of balancing. When a correction weight is added, the machine's vibration vector changes direction and magnitude. Vector addition helps determine the resultant vibration after applying correction or trial mass. The slide covers tip-to-tail vector addition, graphical representation on polar grids, and understanding how vector interaction predicts balance outcomes. It provides the conceptual basis for determining final weight and placement once the trial weight vector is known. This slide teaches vector subtraction, which is crucial for determining the correction vector. By subtracting the post-trial vibration vector from the original vibration vector, the practitioner identifies the vector that must be neutralized with a correction weight. The slide explains head-to-tail arrangement for subtraction, importance of consistent reference direction, and how subtraction reveals the magnitude and angle of required correction mass. Vector subtraction is a fundamental balancing step. This slide summarizes single-plane balancing, used when the rotor behaves as a rigid disk and its unbalance can be represented in a single plane. The slide describes the conditions under which single-plane balancing is appropriate: rotor speed below first critical, short axial length, and known operational behavior. It presents the approach: measure initial vibration, apply trial weight, record new vector, calculate correction mass, and confirm improvement. Single-plane balancing is widely used in fans, pumps, couplings, and other compact rotors. This slide explains the vector process specific to single-plane balancing. It highlights how the practitioner uses the initial vibration vector, trial weight vector, and the resulting vector to compute the final correction. The vector triangle method is described. The trial weight creates a predictable vector shift, and that shift, combined with geometric relationships, reveals the required correction. This method ensures accuracy even in sensitive or high-speed applications. Precision in measuring amplitude and phase is essential for valid results. This slide presents the measurement setup used for balancing. It discusses accelerometer placement, key phaser alignment, cable routing, and instrument configuration. The slide stresses the need for clean signal acquisition, eliminating noise, and correct scaling. It also explains radial versus axial measurement selection, tachometer alignment, and phase reference verification. Accurate setup determines the quality of the balancing outcome. This slide explains the first step in the balancing procedure: recording the original vibration amplitude and phase. It highlights the need for multiple runs, stable speed, consistent load conditions, and verifying repeatability. The original run establishes the baseline against which all later measurements are compared. Proper documentation of vector data is vital, as errors at this stage propagate through the entire balance computation. This slide discusses how to safely apply a trial weight to the rotor. Topics include determining an appropriate trial mass, selecting a safe mounting method, bolting, clamping, adhesive, and verifying balance plane accessibility. The importance of applying the trial weight at a known angular position is emphasized, as incorrect placement invalidates the procedure. The slide also covers expected changes in vibration and how to confirm that the trial weight is secure before the test run. This slide describes how the angular placement of the trial weight influences the vibration vector. Proper selection ensures the trial response is measurable and provides sufficient vector separation for accurate calculations. The slide describes typical reference orientation using key phasor marks and how technicians select convenient mechanical locations. The better the trial weight resolution, angle and magnitude, the better the balance quality achieved. This slide explains how to evaluate the machine's behavior after applying the trial weight. Technicians compare the new amplitude and phase to original values, observe vector shift, and confirm repeatability. The slide addresses typical issues such as insufficient trial mass, inconsistent phase behavior, or poor signal quality. Proper analysis of the trial run determines the accuracy of the correction vector and ultimately the final balancing result. This slide explains situations where the trial weight must be removed: excessive vibration, structural concerns, incorrect positioning, or safety hazards. It also discusses how removing the trial weight allows the rotor to return to baseline conditions before proceeding with further analysis. The importance of re-evaluating the baseline vector after removal is emphasized to ensure measurement consistency. This slide discusses the calculation and application of the final correction weight. It describes converting vector magnitude to mass and positioning the weight at the correct angular location. It also covers the verification process, running the machine at operational speed, comparing final vector with baseline, and ensuring significant vibration reduction. The slide emphasizes checking multiple radial directions, confirming phase stability, and documenting the results for maintenance records. This slide explains trim balancing, performed when a rotor is mostly balanced but requires fine adjustment. Trim balancing is common after maintenance shutdowns, component replacement, or changes in operational conditions. It involves applying small correction weights based on refined vibration measurements to achieve optimal balance quality. Trim balancing typically follows the same vector principles on a smaller scale. This slide explains weight splitting, dividing a required correction into two or more positions, and weight combining, merging multiple corrections into one position. These techniques are essential when rotor geometry limits placement options or when multiple components influence balancing. Splitting helps achieve better distribution, while combining simplifies mounting. Proper calculations ensure vector equivalence and effective correction. This slide illustrates how vector principles apply when combining weights into a single equivalent location. It describes calculating resultant vectors, selecting practical mounting points, and ensuring the correction mass effectively counteracts unbalance. Combining weights is essential in field balancing where mounting options are constrained and precise weight placement may not be feasible. This slide covers the 4-run no-phase balancing method used when phase cannot be measured. The procedure relies entirely on amplitude changes between runs with known trial weights. It is commonly used in simpler fan balancing or when instrumentation does not support phase measurement. The slide details the 4-run sequence, amplitude comparison method, and correction computation. While less precise than phase-based methods, it is effective in limited instrumentation scenarios. This slide explains two-plane balancing, necessary for long or flexible rotors where unbalance is distributed across multiple planes. The slide discusses cross-effect coefficients, trial weights in each plane, and vector coupling between planes. It outlines the differences between rigid and flexible rotor behavior and emphasizes the mathematical complexity involved. Two-plane balancing ensures both ends of the rotor achieve acceptable vibration levels without introducing new unbalanced conditions. This slide describes the step-by-step process for two-plane balancing: baseline measurement in both planes, applying trial weight in plane A, observing changes in planes A and B, applying trial weight in plane B, recording responses, calculating influence coefficients, computing final corrections, and verifying results. The slide highlights the importance of consistent speed, clean vector data, and accurate phase measurement to ensure correct coefficient calculation. This slide presents general balancing rules of thumb. These include selecting trial mass to achieve 30 to 50% vector shift, maintaining clean phase readings, ensuring correction weight distribution matches rotor geometry, and verifying results in both radial directions. Rules of thumb provide practical field guidance that enhances balancing efficiency, reduces trial iterations, and improves outcome reliability. This slide provides an overview of key standards governing balancing quality and allowable vibration. ISO 1940 discusses balance quality grades, G-values. ISO 7919 addresses shaft vibration limits, while ISO 10816 specifies machine vibration severity by class and size. The slide explains that these standards ensure consistency across industries and help define acceptable operational vibration levels. Engineers rely on these standards to determine whether a balanced job meets compliance and operational safety requirements. This slide summarizes the key points of the balancing presentation. It reinforces that balancing reduces unbalanced forces, lowers vibration, prevents mechanical failures, and extends machine life. The summary reviews the critical steps: diagnostic evaluation, vector analysis, trial weight application, correction calculation, verification, and adherence to standards. Balancing is both an analytical and practical field task requiring precision and adherence to established methodology. This slide lists essential takeaways. Unbalance is a primary cause of rotating machinery vibration. Vector mathematics enables accurate balancing. Trial weight selection and interpretation are fundamental. Safety and procedural discipline are critical, and adherence to ISO standards ensures quality. These key points reinforce best practices for engineers performing balancing in the field or in a maintenance environment. This final slide concludes the presentation. It invites questions, encourages professional discussion, and closes the engineering session. It may also include contact information or references for further reading, depending on audience needs. The final slide serves as the natural endpoint for the material covered and allows participants to reflect on balancing methodologies and their importance.